Let's introduce Markov chains, which is how we're going to bring the ideas of time and memory into probability. So consider a sequence of discrete random variables, x0, x1, x2, and so on. And we're going to think that this index 0, 1, 2 represents discrete time. Remember that an infinite sequence of discrete random variables, like the one above, is always described by a collection of joint PMFs. And we'll write that here as P of xt1 up to P of xtm for xt1 up to xtm. And we can pick a joint PMF like that for every possible choice of time indices, t1 up to tm, and any m. So this is a very complex way of writing things, and usually we simplify it. Before, we simplified it through independent and identically distributed random variables, or IID. And the way that that allowed us to simplify the joint PMF was we could factor it. So we could take the general joint PMF and factor it into P of x xt1, P of x xt2, up to P of x xtm. And there was no dependence across time. So now let's introduce a simple way to capture the idea of memory, or model the idea of memory over time. And we'll say that the sequence x0, x1, x2 has the Markov property if for the time indices t1, t2, up to tm, conditioning xtm on xt1 up to xtm minus 1 only depends on the most recent random variable. Okay, so if I write the conditional distribution xtm given the past here, xtm minus 1 up to xt1, then the only thing that stays is xtm minus 1. So the most useful thing, and really the only useful thing for me to predict what's going to happen next, is the previous time. In the IID case, it didn't matter. Everything was independent. If I condition, the conditioning just goes away. Here, if I condition on the history, only the most recent time matters. Okay, so a discrete time Markov chain is just a sequence of discrete random variables, as before we're calling them x0, x1, x2, and so on, satisfying the Markov property. Okay, and some nomenclature, we refer to the random variable xi as the state at time I. And the Markov property in this context is equivalent to the following. So the next state, xn plus 1, conditioned on the full history x0, x1 up to xn, only depends on the current state xn. So if I try to write this conditional probability distribution of xn plus 1 given the whole past, then only xn matters, the most recent point in the past. And we're going to focus only on Markov chains with the following properties. So we're going to insist that they have finite range, or you could call it a finite state space. And to simplify our notation for these videos, we're going to say that the range is always equal to the following integers. It's going to be 1, 2, up to k. So if you had 2 nodes, we'll always label them 1, 2. If you had 3, 1, 2, 3. If you had 10, 1, 2, 3, up to 10. We'll also say it's homogeneous in the sense that the conditional PMF, x of t plus 1 given x of t, is not a function of t. So the way that we jump from time to time doesn't change with time. Only the values that I plug in matter. Okay, the values of xt plus 1 and xt. So some applications which you could ask about or read up on are Google's PageRank algorithm, models for population genetics, epidemics, speech, network traffic, so traffic on the internet, mathematical finance. There are many different areas that use Markov chains. Okay, the transition probabilities for a Markov chain, which we write as pjk for j and k in this range, that is the probability of going from state j to state k in a single time step. So specifically, when we're writing p of xt plus 1, given xt, and we want to go to k at t plus 1, and we start at j at time t, that probability is just pjk for all t. These probabilities are non-negative because they're probabilities, and they normalize. So if you add them up, summing over k, because k is where you're going, you get 1. And it can be really useful to visualize Markov chains with a diagram. So this is how we do it. First, we draw, so let's say we have two nodes. We're going to draw a node for each state in the range. So remember, we're always writing the range as 1 through k. In this example, just 1, 2. So I'm going to draw 2 nodes, and I'm going to draw out the transition probabilities here. So I have 4 transition probabilities. For each positive transition probability, so everywhere where the transition probabilities are positive, pjk is greater than 0, I'm going to draw a directed edge from node j to node k. I'm going to do that here. So I have red, blue, purple, and orange. And that corresponds to those 4 positive values, 1 to 1, 1 to 2, 2 to 1, and 2 to 2. And I'm going to label each of these edges with the values of the corresponding pjk. So here the red is going to be labeled with the probability of p11, which is 1/5, then 4/5 for blue, 3/5 for purple, and 2/5 for orange. We're not going to draw an edge if pjk is equal to 0. Okay, and so note here that the outgoing edges have to sum up to 1. That's normalization. So the edges leaving 1, 1/5 and 4/5 sum up to 1. The edges leaving 2, 2/5 and 3/5 sum up to 1. Let's do one more example. This time I'm going to have 3 nodes, and I'm going to give you a big list of transition probabilities, this time including some zeros, so we can see what that looks like. Okay, so here's a big list. And so I'm going to draw my 3 nodes, 1, 2, 3. I'm going to draw an arc from 1 to 2 and 1 to 3, because those are the positive probabilities leaving from 1 going to somewhere else. I don't draw an arc from 1 to 1 because that probability is 0. I don't draw an arc from 2 to 1, again, because it's 0. But I draw one from 2 to 2, I write 1/2, and from 2 to 3, I write 1/2. Finally, another one from 3 to 1. Okay, and that's the full set of arcs that I need to draw. Okay, the initial distribution is the marginal PMF of x0. So at time 0, what's the probability of being in a certain state? And if that p of x0 is 1 for some value and 0 for all other values, then we'll say that A is the initial state because we're always starting in state A. Okay, and so if you know the initial distribution, right? So if someone tells you, or you derive somehow p of x0, and you also get the transition probabilities, p of jk. So if you know those 2 quantities, then you have a full probabilistic description of the Markov chain and how it evolves with time. And that's all you need to work things out. Okay, let's look at what these Markov chains look like in their behavior. Okay, so we're going to look at what I'll call sample paths for these Markov chains, and we'll focus on just range 1, 2 and initial state 1. Okay, so here's one Markov chain, an edge with 1/4 between 1 and 2, 3/4 to stay on 1, 1/4 from between 2 and 1, and then 3/4 between 2 and 2. Okay, so what we're going to see, like here's one possible realization that you could think of as kind of typical, is that it'll linger on 1 for a while, and then jump to 2 and linger there, jump back to 1, jump back to 2, and it'll kind of stay. And the reason is it's more likely to stay than it is to switch. Okay, here's another example where I see half on each of these edges. And so there's no preference to stay or switch. And I'll actually see something that kind of looks like an IID sequence. And in fact, it is an IID sequence because there's no memory here. I don't care whether I'm on 1 or 2. I always have an equal chance of going to 1 or 2, it turns out in this case. What if I have a high probability of switching instead of staying? Then I'll always see it switch, and once in a while I'll see it stay. And finally, what if I never see an edge going from 2 to 2? So, sometimes I'll stay on 1, sometimes I'll jump to 2, but I'll always go back to 1 right away. I have no chance of staying on 2. So you can see some really interesting behaviors from these Markov chains depending on what these edges look like and their probabilities, and you get a much wider range of behavior than you would have seen with IID distributions. Okay, so these transition probabilities, which were given, those are telling us the probability of going from one state, let's say state J, to another state, state K, in one time step. So what about the probability of going somewhere in 2 or more time steps? Well, those are just called the n-step transition probabilities, and they're written as P, J, K of n. Okay, so all it's saying is it's the probability of going from state J to state K in exactly n time steps. Okay, so it's the probability of xtn plus n given xt. That's exactly what it is, just going to K from J, and that's for all t. Okay, so P of jk1 is just P of jk. Normalization says these have to add up to 1 if you sum over K. And you can figure them out using these equations called the Chapman-Kolmogorov equations. Okay, and so here's the general form. So if you want to know P of jk for n plus m, you just sum up from 1 to k, this I term, and then you can have n and m kind of split up in this way. Okay, so let me show you an example of how you can use this. Basically, you can use any splitting n and m of the term you're interested that you want, and it's easier to see it through an example. Okay, so here's an example. I want to know the 2-step transition probabilities for the Markov chain we were working with earlier. So that was just this chain, and I want to know P of jk2, and I know P of jk1. So I'm just going to use that. So I'm plugging in 1 for n and m here because 1 plus 1 is 2. Okay, and so I'm going to get these terms. So I'm going to get P of j I1, P1k, and P of j2, 2, and P2k. And so here I'm just adding these terms up. Okay, so for this, I get a fifth times a fifth plus 4/5 times 3/5. Okay, and that's 13 over 25. So what did I do here? Looking at that diagram, the only way to go to 1 in 2 time steps is either to stay on 1 twice or to go to 2 from 1 and then come right back. Okay, so that was P11 times P11 plus P12 times P21. For P12, how can I do that? So it's P11 times P12. So I could either stay on 1 then jump to 2 or go to 2 and then stay on 2. So I can just multiply those probabilities and add them up. And here I'm going to get 12 over 25. What about 2 to 1? So again, to do that in exactly 2 time steps, I either go to 1 and stay, or I stay on 2 and then jump in the next time step. So that's 3/5 times 1/5 plus 2/5 times 3/5. And that works out to 9/25. Finally, to stay on 2 after 2 time steps, so that means either going to 1 and coming right back or just staying on 2 the whole time. And if you work this out, then you're going to get the remaining probability, which is going to be 16 over 25. Okay, so 9 plus 16 is 25. 13 plus 12 is 25. Okay, so that works out.